Yeah, okay. So we have some guests here, and also Ian is a little bit late. So just to tell you the story, what happened on Monday. So what happened is that we have very funny setup of audio system. So this microphone only work for the room.
Oh, okay.
We have 3 more microphones. They work for the video.
Okay.
So we actually video all the conversation. Our plan is that we want to make it to be public online later. So that's why if you want everyone in this room to hear, you need to hold this microphone. And if you want your sound all recorded nicely and could be published online, you need to hold the other 3 microphones. It's one of them. Okay. So this is what happened. Okay. So sorry for this complicated setup. Yeah. Yeah. So we can pace around.
So this is video only?
This is video only, yes. Yeah, this is video only as well. Yeah.
Let's see. So this is not going to be any fun if, period. Now, this is not going to be any fun if people don't sort of ask questions from the audience. I want to encourage folks to do that. It's a relatively short panel. It can be, we only have about 40 minutes. And so my thought was we have 3 experts from industry, Intel, Microsoft, and NVIDIA. And we have 1 expert in software and 1 expert from the sites themselves. And so my thought was we could have a couple, we could do this in a lot of different ways. But I thought maybe this is a talk on the use of heterogeneous resources. And I thought maybe I'd propose a scenario and people could talk a little bit how they'd like to address it. Imagine you met a group of people, nicest group of people you could imagine, who over the course of the last 20 or 30 years have written their software using 800, 1,000 relatively unskilled programmers, and ended up with a big monolithic thing, which they were used to running on the fastest single CPU they could find, where it all ran together in a big loop. And then they were confronted with a situation where within 7 to 10 years, they needed to have about a factor of 100 increase in their computing. And what they were given from technology was a series of independent, faster tools they had never seen before. Are they doomed? And how should they go from where they are now to a situation where they actually stand some chance? Oh, by the way, a little bit of complication. They have the same amount of money they have now. No additional resources. Asking for a friend. So I was hoping that the industry guys could start with talking about sort of like how they expected this to work, and what the tools, what this hardware that they have is sort of designed to do, and how we could make that work in our environment from an application and from a facility perspective. I'm going to. I actually want what I want speakers to do is when I hand them the microphone, they're going to introduce themselves and what they are expert in. I'm going to put you on spot.
I'm Daniel Lowe. I'm a research hardware engineer at Microsoft, working on Project Catapult, which is our project on deploying FPGAs to the data center. These days, a lot of the focus around that is on deploying deep neural nets on FPGAs. Should I keep doing introductions?
Actually, no, we should, if you can talk a little bit about sort of, like, so you're an expert in deep neural nets. Is the idea that we should make all of our problems look like deep neural nets if we want to take advantage of the hardware?
That would be one way to take advantage of the current hardware. I don't think it's necessarily the best way if your applications fall into that.
What would be the best way?
So, I mean, it's an interesting problem you've raised, and I think it's one that we've seen multiple times. These FPGAs are quite new. It's not like there's necessarily IP or libraries out there to solve, to code for these FPGAs to run the applications that are out there. So we've done this with different partners, mostly within Microsoft, where they come to us with, millions of lines of code that is written by many different people, hopefully skilled, but who knows. And it's essentially a process where we take these things, we profile them to see what the hotspots are. We look at the hotspots. We see which of those are applicable to FPGAs, and then we work with them to develop FPGA images to accelerate those parts.
Actually, let's follow up. Yeah, actually, that'd be great.
I didn't know that was an option.
Introduce yourself.
I'm Jeff Hammond. I work in the data center group at Intel. I am a chemist, quantum many-body theorist by training. I've been a supercomputing jock for the past, I don't know, 5 or 10 years. And I work on a wide range of things. My day job is doing something called co-design for supercomputers, so doing sort of architectural and software evolution in conjunction with customers, many of whom are physicists. And one of the things I do think about a lot is the heterogeneity problem. So I guess maybe the proper response to the prompt is lots of people have that problem. It's not just whichever unnamed community you're referring to. I was thinking, oh, are you talking about the nuclear weapons community, or are you talking about the chemists, or who, biologists? Everybody's. I think
the nuclear weapons community has more money. But
they also have more code and a slightly larger problem with experimental reproducibility. You think your experiments are expensive? Anyways. Yeah, exactly. So, as an Intel person, I'll say, obviously, because people still write or have code that runs sequentially, we think we build the best single-threaded performance processor that exists. And we obviously sell them in a way that allow people to buy a part with different things. You could buy a Skylake Xeon with 28 cores. You pay a lot of money and get one that runs up to 4 gigahertz. If you're latency limited and you're a banker and you have spend $50,000 on a suit, you can spend $50,000 on a rig and to get the lowest latency you could possibly imagine. On the other hand, you put money into your software, you get concurrency, and you scale out. And then if you look, you go from Xeon, you go to Xeon Phi, has lower frequency, higher parallel performance, and then of course, we heard earlier today, we have FPGAs, we have the Nirvana stuff. We have more products than I can keep up with. But obviously those things are specialized, and some of them are more or less heterogeneous. My ideal is, of course, don't be heterogeneous unless you need to, right? Heterogeneity should always have a purpose. There should be something, you should have an Amdahl's law argument or whatever, the equivalent of Amdahl's law, Pareto optimal, whatever, for why you specialize. And if you have general purpose compute, you should use the general purpose processor. If you have specialized compute where you've really done your homework and you know why you want to build an ASIC or why you want to specialize, an FPGA is a great option. But FPGAs are not highly programmable in their current form. And obviously graphics, it'd be professional malpractice if I denied that NVIDIA was capable of building some interesting stuff.
Would be embarrassing.
Well, I can admit things. But, so one has to think all about the trade-offs and do end-to-end analysis. And I guess the only thing that I'd ask anybody who's studying this problem is be objective about it. If you're going to compare something, compare it all fairly. So make sure that you write really good CUDA code, and make sure you write some really good OpenMP code, or whatever variant of code you're writing. Write the best code and compare the best code. The thing that makes me want to light myself on fire in the parking lot is when people write really good CUDA code and then they compare it to 1986's finest punch card, Fortran 77, that assumes a single-issue superscalar processor, and they don't even touch it. And also all the data is in common blocks and refuses to vectorize. And then they go, oh my goodness, GPUs are so amazing. That's crazy. It turns out you can win with a GPU and you can win with a CPU, but you should always do an objective comparison. If you really want to run your punch card Fortran, please also write the worst CUDA you could possibly imagine. Insert printf in every single line to make sure that it's a fair comparison. Anyway.
That's a very specialized.
I think I have both of these figured out now. So I'm Tom Gibbs. I'm from NVIDIA. I manage developer relations for NVIDIA globally and have been in high-performance computing for quite some time. I actually wrote Fortran code on punch cards in 1978. So by 1986, I think they were done. But in 1978, I was still programming Fortran code with punch cards. So I wrote my first simulation then. I wrote my first AI code in about 1982.
And I started in supercomputing probably about the mid-1980s. So I have a historical perspective on the community. And Ian, this isn't the first time. We are encountering change right now as a community. This isn't the first time that happened. The weapons community, and in fact the entire HPC community, went through a bit of a nuclear winter in the early 1990s when the Cold War ended. And the funding for big, giant, monolithic vector machines stopped. And the shot heard around the world in the mid-1990s when the National Science Foundation stood up and said, we're not buying any more vector machines. And, you know, that there was no OMG back then, but OMG was the reaction from the community. What do you mean? Oh, we have to write code for these big, massively parallel things with microprocessors in them. And that was a huge for the community. A lot of hard work had to go into refactoring code to take advantage of that architecture because the money to go buy big vector machines ended. In this case, you know, we're going into a new era of change, and that era of change wasn't introduced by an outside source necessarily. It was just physics. Physics just ran out. You know, Dennard scaling ended about 10 years ago, and we just can't continue to push single-threaded performance like we were able to push it as, I wouldn't say easily, but as readily as we were able to push it. And so now as a community, we have to come together and embrace the fact we have to do some different things. So one of the things I'm responsible for, kind of an initiative that in NVIDIA, they kind of point people to do different things, and one of them for me is the convergence of HPC and artificial intelligence. So to the question, what would I tell somebody to go do? So I think for conventional high-performance computing applications, you know, the two boundary conditions really are data locality and compute intensity. So you need to look at your application, and if you can find hotspots, that's wonderful. If you're running a code like Giant, you probably don't have any hotspots, so that's a problem. You may have to re-architect some part of the code so you can get it to the point that you have data locality and compute intensity. And you can do sort of your own roofline analysis on that and say, well, where are we? And what kind of performance do we think we're going to need? And if you don't really have data locality and you don't have compute intensity, you can head down a path of trying to do some, you know, refactorization of the code. At the same time, there's this new thing, and the new thing is AI and deep learning. And that may apply. And where it does, we see some pretty interesting opportunity, and where you can get not 1, 2, 3, or 4 or 5x, but 2, 3, 4, or 5 orders of magnitude in terms of the time to science if you can apply deep learning to the problem. So that's another avenue. But I think, you know, the short answer is it's going to take some creativity because there's not going to be an easy path. On the other hand, I think this community with the 800 programmers or whatever you said, they did it once before. I think making the move from monolithic shared memory vector architectures onto distributed memory multi-computers, they made it from fully proprietary on-prem to grid. And I think we're going to take a same kind of quantum leap as we go into the future.
But I'd like to sort of ask a follow-up question, and this maybe goes to facilities. One of the things the grid benefited from was that if you look at it's geographically distributed, but it is incredibly homogeneous in terms of the architectures that are used, even the amount of memory per core. It is effectively a cookie cutter 200 times globally, more or less. The architectures, none of the hardware is more than about 3 or 4 years old. It has the same Excel, and we typically make a single copy of the application which is optimized for a particular platform, and then it is distributed out. And so when one talks about sort of getting the big improvements out of something like AI, when you have to run on a relatively specific set of hardware, we have to have the hardware optimized for the network that gets produced. Is the vision that this kind of applications would run everywhere, or we would have sort of specialized facilities designed to do a particular thing? Because at the moment we have very general facilities designed to do everything.
Yeah, I'll pass this down, but when we talk about AI, I think it's important to distinguish training and inference. Mm-hmm. And the good news is on the inference side, you don't need specialized hardware. I mean, you can benefit from it. You go buy some GPUs, you're going to run a lot faster. But you can generally get the performance gains of, the orders of magnitude of 3, 4, 5x orders of magnitude. Those are generally CPU running simulation code, conventional, to CPU running the neural net. Now, you want to then add that on the GPU. It runs 10 times faster yet again. But you're making a huge performance. So I think really you get one of the benefits of the AI. Once the network is trained, inference generally tends to run pretty well and doesn't generally require a lot of processors to run the inference. You just run a lot of it.
Okay.
Yeah, well, I will say on this, as we heard earlier today, I mean, we're putting a lot of effort into the frameworks. So my hope is, I've been in so many science meetings where people they're like, I want a BLAS for that. I want a BLAS for chemistry or BLAS for whatever. And I've worked with a lot of the people who develop BLAS, and I sort of cringe because linear algebra is more fundamental than any domain science by definition. But I think that we will, hopefully the whole community will evolve to the point, and I always say this, people who buy hardware should embrace open standards and open frameworks, and then let our respective, production groups duke it out, right? Write code to TensorFlow, write code to Keras, or whatever it is, Torchiano, Caffe, all these different things, and then use that as your portable abstraction layer. I would say don't write code to CUDNN, or frankly, don't write code to MKLDNN, because then you don't have an objective way to go after these things. I would hope that everybody puts the energy in to making sure that these frameworks are a portable abstraction for that community. I don't know what it takes to make all of your software. I mean, I think particle tracking, probably it's hard to write that the best way for every architecture. Or if you do it by brute force. But I think the grid is relatively homogeneous. But I was at a facility before I joined Intel. I worked on the Blue Gene, and it was always really painful to get somebody to move from a Xeon to a Blue Gene, or it was basically the Blue Gene Q at Argonne and the Titan, which was AMD and NVIDIA, and those machines were wildly different. And then NERSC came along with the Xeon, and it really, people just went to the center that had the thing they want. So I think we may face a future where the grid itself, all these different facilities, is a little bit more heterogeneous. I can say, having programmed a lot of different architectures, even if you exclude the GPU component, if the non-Intel world, if AMD and ARM and whatever RISC-V and all these things start producing server parts, people will have to pay a great deal of attention. There will be some things that are just portable, and there will be other things where you need to design frameworks in such a way that you can have a dynamically loaded plug-in that fires up the right set of kernels for whatever you're running.
Do you want to comment on that, David? From a software perspective?
Sure. So I'm David Lang from Princeton, and I guess Ian called me the software expert on the panel, which he certainly left out the word HEP, at least in that context, I think. Actually, part of what is being suggested, I think, involves throwing out the millions of lines of code that we have, which is certainly a nice solution if we end up with a completely deep neural network-driven environment. We have a lot less code to maintain. That would be great, I think. Maybe not for the job security of people in the room, but for the ease of use in the field, if it all becomes evaluating networks on, and the work goes in the training instead, which is easier to imagine doing on a specialized hardware where you can avoid some of the grid complexity that way from a user point of view.
I'd like to sort of, I am a big proponent of trying out neural nets and deep learning, but maybe a show of hands for the audience. As a big proponent of neural nets and artificial intelligence for our kinds of science, it also occasionally feels to me a little bit like a lifeboat. like we have we don't have any solution for what we're trying. We have this giant problem. We have no solution. Here is artificial intelligence. Everything will be fine. If you had to bet we're going to succeed in making artificial intelligence as a replacement for the primary way that we're working, raise your hands. Oh dear. Unconvinced.
So I think Tom probably spends more time thinking about AI analogies than I do. But one of the things I think is, at least the deep learning stuff is, right, there's training and then there's scoring or training and inference. And one of the things to make that pipeline work is you have to be able to train. Some things you can train, but you have to have data to train. So for example, with cars, it's not hard to get data. You put a camera on a car and you pay somebody $12 an hour to drive it around for like 5 years, and then bam, you build a self-driving car, because you will have seen cats run across the road and balls get thrown and people run red lights. I don't know that much about particle physics, but it seems that a lot of the things you're looking at are rare events. And I wonder, do you have enough events to train networks? If you only observe, I don't know, how many times have you actually measured the Higgs or whatever it is? Is it a billion times or 1,000 times or 12?
I think it's about 80,000 times, something like that.
So I will say this purely as a question, you know, if you have the data, then you can train. But if you cannot train things on nothing. So you have to sort of bucket your problems into where you have lots of data and you can think about training. Or, you know, if it's just a person, if a grad student stares at a screen 12 hours a day looking for blue dots, right? Okay, yeah, you could train a neural network to find a blue dot on a screen. But there's a bunch of things you can't train a computer to do.
Coincidentally, they would be happy with the $12 an hour. Yeah.
Yeah, unfortunately, they only stay on task for about 3 years, and then they graduate, and then their rate goes up. Or at least that's what they tell me. So first of all, if it came across that way, let me just say I don't think anybody should be throwing out their 40-year under development HPC applications. And while some of the things that I did in the late 70s and early 80s were AI related, actually I wrote Kalman filters that went on airborne radar systems, so I'm pretty tapped into all that too. And you know, I spent most of my career doing conventional HPC. So I think the point is that whatever you're doing today, or whatever you did 10 years ago, you're going to have to do something different now. So just like you couldn't write the same code you wrote on the Cray vector machine with a high-speed scalar processor that had, you know, single-cycle access to main memory, that was really great, you know. That all went away, and so you had to do something different. So now you have to do something different too. So the only point is you've got to, you know, artificial intelligence introduces a choice. It's not necessarily the answer, but if you're either going to follow that path, and maybe you do both, you'll follow that path, or you're going to have to probably refactor and optimize your code to take advantage of a heterogeneous architecture if you want it to continue to go a lot faster, because if you don't do that, you're probably not going to go much faster generation to generation. And there's a procurement on the street now in the U.S. from the National Science Foundation where they basically said, you know, our last generation National Science Foundation leadership machine, we spent $200 million and it ran so fast. Well, we're going to spend $60 million and it needs to run 3 times faster. And when you do the math and you look at the suite of applications, you're not going to get there with a serial processor. And I think the RFP was kind of designed that way. So essentially, whatever you do in the future, you're going to have to do something different. And then the question is, where do you want to put your energy?
Right.
And you know, I think all the companies, the focal point, whether it's FPGAs, whatever the flavor happens to be, they're doing things in the tool chain to make it easier, but still going to require effort on the part of the 800 people to do something different.
Well, kidding aside, I actually think we have a big sort of branch in the road to get through, which is going to be terribly complicated, which is that we're in a situation where it'd be fantastic if what came out of the detector is 10,000 events per second, and we had a neural net that did a categorization of those events in real time. This would be a real change in the way that the field operates. And in some sense, we have all the events to train on, and things that we knew about could be categorized in interesting ways, and things that we didn't know about might be the most interesting events. If it turns out like something that's incredibly rare and was unable to be categorized, that might be it's a physics discovery machine. It's a brave new world. Now, the trouble with that is that it's kind of, well, it'd be fantastic. The chance, we don't have any idea if it would work. And so the problem we've got is we have industry which has done a lot of optimization to solve a particular deep learning problem for lots of other people, also up to including running lower precision because it's more helpful for the kind of applications that other people are running than high precision applications that are run in science. And we have to make a choice in terms of where we put our development effort, because in 7 years we have to have a system that works. And so in some sense there's a bit of a disconnect for me where I have fast hardware that does a particular thing, but I'm not sure it's applicable to my application, and I don't know how to get from here to there. I don't know how to get from there from a software perspective. I don't know how to build a facility that's got enough tools that I don't have the risk of failure. It's a multi-billion-dollar program, and I don't have normally we sort of run with a not guaranteed success, but we have a plausible plan, and it feels to me like there's some holes in our plan at the moment.
So I think one of the things that to me is neat about the machine learning revolution is that it has created a totally new economic incentive for developer tools. If you think about historically, why did the U.S. government, DARPA, and all these agencies pump so much money into computing? If they didn't spend that kind of money, nobody was going to build these things. And now I was at a meeting with the nuclear weapons people a while back, and they were saying, well, maybe we should just ride on the coattails of Amazon. And I told them, well, don't go too crazy. You guys still have pretty good ideas. Please push yourselves. We need you, because the cloud isn't doing everything right. They're just doing some things right. But I think that one of the ways that this community can increase its chance of success is leveraging as much of that as possible. I look at the amazing progress that has gone into just Python software. Like, Python used to be like, hey, it's nice and quick and dirty, and you can script like crazy. And now it's like, oh my goodness, we have commercial, just-in-time compilation tools. People make money off of making Python go faster because these data scientists, that's their bread and butter. So I think that, don't rewrite everything in Java or Scala or MapReduce or whatever thing just because, but gravitate away from things that are boutique to the high-performance computing world. I mean, I happen to like Fortran, but the fact is there's going to be a hell of a lot more progress in C++ and Python over the next 20 years than there will be in Fortran. It's just a fact. And that's something that you guys can leverage. The other thing that somebody was asking me a while back about what they should do to sort of, what's the next cool thing? My company is going to move heaven and earth to make 10, 15, 20%, compound annual growth rate on CPU performance. But one of the places that you're seeing sort of really easy Moore's law or better is in storage and memory technology. And of course, if you're data analytics people, well, I heard petabytes come up multiple times. We have this 3D crosspoint stuff, which I haven't played around with yet. But you look at SSDs. I have two laptops. One's from 2014 and one's from 2007. And the CPU runs about the same speed. One of them has a hard drive that I can hear go ka-chunk, ka-chunk, ka-chunk. And the other one is a Mac that boots up in like 2 seconds. And the difference is storage. And this is something where if there's software, you can modernize all your compute software, and that'll get you mileage here. The other thing you could look at is, what if I modernize all my I/O software to take advantage of non-volatile byte-addressable memory instead of tape drive-like design spinning disk?
And maybe we should go to Roy for a second. Yeah. What's that? No, I was going to Roy, just from a...
Can I make one comment?
I was actually going to ask you to make a comment, but you want to make one comment, but also make a specific comment, is that from a facility perspective, when people are talking about sort of how to optimize this, we tend to optimize specific things, but you as a facility have to support a variety of communities. And so what are the sort of the things that you worry about when either talking about specialized capability like enhanced I/O or specialized processing capability?
I will answer that second.
Sure thing.
Because I have another point that I would like to make, because actually you brought this up when you were talking about Dennard scaling. So about 15 years ago, that's what I was doing, was effectively doing semiconductor devices. And what I see that's interesting, being a kind of outsider to the community, is the same thing that was going on in the semiconductor industry about 15 years ago, where people were panicking and saying, well, we've been scaling transistors traditionally for the last 30 years, and it's been working perfectly, and that stops. And you had people coming out with SOI, you had people coming out with 3.5s, all of these different types of transistor, and we finally have settled where pretty much everybody is now moving on to FinFETs or waffle FETs. And this is the big thing, right? That we've got these wraparound gates and everything's working. And I see kind of the same thing happening. There's all of these different things that are going on, and we're trying this and trying that and trying the other thing. But we'll probably find something. Right? We'll settle on something. We will get there. And the thing that I was finding most interesting from the talks that I was seeing today was the generative neural network algorithms, I think, are the things that have quite a lot of legs. The ability to actually create something from a neural network, I think, is pretty cool. So that's what I wanted to, that was the comment I wanted to make. Now, from a facility standpoint, it all comes down to cost, right? We run these facilities and are desperate to keep them loaded. The thing that keeps me up at night, and I will wake up at 2 in the morning and check the cluster to make sure that we're running jobs, right? If at any point we stop.
There's medication for that.
Yeah, it's called checking the monitoring and then go back to sleep. So in the UK, we have a competitive funding model. So if I'm not running work, I lose out on research funding. It's as simple as that. The less work that I run, the less money I get. And then you get a fixed amount of money and you have to decide what you're going to do with it. So any time my cluster's not running work, I'm losing money. So the investment in any of these new technologies has to be tensioned about the fact that if I'm not using it, I'm losing money. So from a facilities perspective, software comes first, right? There's got to be things that we know are going to be run and are going to be run consistently and are going to be able to fill up the facilities that you buy. And you've got to be careful, again, because, you know, an FPGA or a graphic card is a non-trivial amount of money. I think I ran the numbers on the Tesla P100 just for fun, and that will buy me 2 work notes, or that will buy me 100 terabytes of storage for just a single card. That's not even including the chassis costs, right? So that's an awful lot of investment in a device that I'm not entirely sure I'm going to be getting lots of software in to run. That can go into additional storage. WLCG still says that there should be 2 gigs of RAM per core, even though everybody wants 4, right? So you've always got to increase the memory cost. Just recently, we have lots of problems with payloads not having enough IOPS because we're still using spinning media. And so there's that. We're not going to ask for anything other than spinning media, but it'd be really nice if you had SSDs in your machine. So suddenly now the storage cost is going up. And it used to be, you know, £50 a terabyte, and now it's going up to £100 a terabyte, £150 a terabyte, because you've got to look at SSDs. So I'm really excited because, as I said, coming from a different industry and looking at it, I see this period of uncertainty as a cool thing because you get to play with lots of interesting technologies. There's new things that you can do. But we've got to be careful to try and identify those and then be able to use those consistently. And as I said, you know, fast simulation using generative neural networks I see as being a really cool thing that potentially could fill that.
Thanks. Are there questions from this side? You people are worthless.
I want to ask a question about cloud adoption, because, you know, this is one place where, I've gone through the math with some chemists, and, you know, the chemists have figured out a workflow, many of them, that they can do 80 to 100% utilization. They just have a script that runs, you know, every molecule on the, you know, they can come up with, or they run more iterations or whatever. And for that, for them in that environment, the cloud does not make sense. However, if your utilization drops below 50%, the overhead of the commercial cloud actually becomes economically viable. And I have a friend down in Australia at a facility, and she said they sort of do a hybrid model where they have their own iron, and then they have basically some way, and I don't know how they do it with the software, but they offload to AWS whenever they go to 100% cap. And I guess I'm curious, sort of, does that work with your infrastructure? Does it make no sense because it's too expensive, or because they don't have the right stuff?
We fill the cluster constantly. We did an cost, so again in the UK we did a cost analysis in this. For the amount of money I get for 2 years, I could run the cluster for 1 month in the cloud.
So, but you said something that you don't want to adopt GPUs because you're not sure they're going to utilize it. I mean, for some sort of like if Microsoft Azure had FPGA HPC cloud,
yeah, I mean,
you
so
adopt that because you don't know that you're going to get 80%
that and that
utilization.
that potentially could be some sort of path to market, right? You use those cloud resources to test and to build out the software stacks, and then when you're happy that those software stacks will run consistently, we can bring them into the data center and save money buying the hardware and running it ourselves.
It would also be an example of a place where if we were able to get factors of 100 or more increase in performance, that it would make sense then to run those on rented resources, because we wouldn't be able to keep them busy for the entire year. So if there was such an acceleration that we weren't able to keep a resource busy for the whole year, that would be fantastic. But that would be a place that would make sense to rent, even if the costs were much higher. I had a question also. I want to pass it back to, oh, go ahead. Sure.
You raised a point, Ian, about risk.
Mm-hmm.
He said, yeah, well, you know, the last, say, 10 years ago, if you were embarking on a project, the chances that it didn't work were pretty low. Well, so we're in a different time now. So how many people feel like they could take risk, like they try something and it didn't work? Okay, that's good. When I was at the Pixie conference, I gave a talk earlier this year, and one of the postdocs, we were talking about the convergence of HPC and AI, and he said, well, you know, Tom, geez, you know, I got to publish science to get my PhD. I can't take a risk. And I think one of the things, as we enter this era, we're in the era now, we're not entering it, we're in it now, we will have to take risks and fail fast, because we won't necessarily know that we're going to be able to get enough performance out of the conventional method, and maybe we can. And, you know, again, I'll reiterate, I'm not saying that the whole answer is AI, it's just something to be explored. One thing to explore, but the other thing would be, can you get performance out of the conventional approach? And, you know, if it turns out you can get enough performance out of the conventional approach and run on a CPU, rock and roll, because that's going to be the easiest path to success down the road, if that will work. So, you know, you've got a broad landscape right now, which is the problem, or the benefit, because you're not locked into one type of solution. In many ways, moving off the vector machines, you didn't have that many options. And in this case, we've got a lot of options now, but we may have to take some risk to be able to get there from here.
But I think it's an excellent point, and I think it's a good. I'll hand it to you. But I think one of the take-home messages needs to be, how do we figure out as a community how to chase something down and sort of guarantee that it sort of just make a decision as to whether it's possibility or not relatively quickly, which is something we've had a really hard time doing, in part because it's quite difficult to prove that something's impossible. If you succeed at it, you can prove that it was possible, but you don't know if you just weren't competent, or if there was something specific about the problem that caused it not to work. So I think we have a hard time declaring something as not possible and moving on to the next thing. But go ahead.
I have a comment, no question. So Ian, when you introduced the topic, you were saying that the WLTG is homogeneous, and we want to make it somehow to understand how to make it heterogeneous. Now, it was not clear at which level you mean heterogeneous. I mean, it has to be heterogeneous at the level of the cluster. It has to be heterogeneous at the level of the grid. You want to have a data center just with GPUs, or you want to have some racks with GPUs in the same data center. You want to have, I mean, now the question.
Okay.
We, in CMS, we are trying to exploring different heterogeneous opportunities, and we are exploring GPUs, we are exploring machine learning, we are exploring fast inference with FPGAs, we are exploring many different things. And one of the problems is integration. I mean, when you are designing the high-level trigger farm of round 3 or round 4, what do? You add every type of every accelerator to each node? Do you design the farm so that it has a very dense rack of GPUs? Then you have to redesign the framework so that it can offload remotely the jobs. How do we solve this problem? I mean, there will be many different accelerators for many different things, compression, decompression.
So that actually was my comment about what it means for heterogeneity, is because at the end of the day, I don't actually care about heterogeneity as a general concept. I care about not failing miserably. David cares about failing miserably.
The reason CMS is doing those things is because CMS would like to save money, right? And run its HLT farm, for example, using GPUs, because it's showing, thanks to you, that it's cheaper to do it that way. And that's the sort of study, I think, that has to start the process of sort of software coming before the facility. And then, indeed, the hard part is perhaps going from the guy doing software R&D to how does the software get put into the production software stack with all the caveats that you talked about, and then goes the facility. Even a perhaps more challenging question is if facilities start buying things that another experiment wants, and you're told, well, gee, shouldn't you be using this thing too, even if your software isn't prepared for it? And that's I think a scarier question from the software development point of view.
Okay.
So I think there's a bunch of interesting things that I've seen and learned about as I've become a vendor, and I talk to customers, and it's important, I think, to recognize in some of these computational technology, progressions or experiments, which is the horse and which is the cart. And a good example of this is in the nuclear weapons complex. There is a strong desire to push the edge. So there's a recent interview about this, that their production science is done on, CTS, commodity something systems. I can't remember, test bed systems or technology systems, commodity technology systems. It's all Xeon with Omnipath or InfiniBand. But they also want two crazy machines on the edge, but they don't want them super crazy where they're unprogrammable. But they're whether it's Blue Gene or GPUs or whatever, and they're not necessarily buying those because they think that's absolutely the best for the production. It's just that they need to drag sort of legacy codes kicking and screaming into the modern era. And I think that the way that this experiment should play out in any scientific community is recognizing that you need to buy a set of systems to run the work. You go to war with the army you have, so you have to go to simulation with the codes you have. But then you also have to have this experimental thing. But it's really important to separate these two and see how they're different. Because if you go out and say, okay, we want to run the experiment of can we run on some sort of fancy new architecture, but you confuse your users into telling them that that's actually the day-to-day production system, then they get mad. Usually you end up getting a bunch of people who hate you for decades because they've been bamboozled into using some architecture that they were told was going to be the great next best thing and that it would just work, when in fact it wasn't supposed to just work. It was supposed to be a window into the future. And I think for a lot of this, you know, we have to just be very judicious about where we, like, how big of bites we take. You know, I don't know much about FPGAs. I've never written serious code to them, and I would absolutely not want somebody to deploy a production facility in a supercomputing center for scientists composed primarily of FPGAs. But I think it would be fantastic if a bunch of people took that leap with some sort of cloud environment or with a testbed system with 8 nodes.
Well, actually, I wanted to go back to a comment that you made, a Microsoft comment earlier on. The idea of taking people's large stacks of code and optimizing it for a piece of hardware they've never seen, this is not a model that we've worked in the past, but it is sort of an interesting model. Is this the way that people, is this a direction Microsoft wants to be in terms of optimizing large stacks of code to run on hardware? Is this the business model for them? A revenue source?
Probably can't speak much about business models.
Okay.
Yeah, I don't know much about that. But I mean, to your point about optimizing on sort of unseen hardware, I mean, it is certainly much different than CPUs traditionally. But I mean, in some sense, when you move generation to generation of CPUs, there is optimization to be done there, right, for cache sizes and processor speeds, and things like I/O as they come out. I mean, I don't think it's an entirely brand new concept. Certainly the languages maybe and the frameworks and the target devices have changed, but this idea of optimizing for new hardware, I don't think should necessarily be that of a new thing to be scared of. I want to circle back on this comment about the heterogeneity, because I think it is a really good comment in the idea that I think a lot of us here believe that heterogeneous systems are coming to become more prevalent, but I don't think the vision is necessarily that you're seeing hundreds of different heterogeneous chips that and you move data center to data center and it's all completely different. There is still a large value in having some level of homogeneity. So for Microsoft specifically, the model we've gone with the FPGA is that we have traditional Xeon CPUs and then an FPGA attached to them over PCIe. And this is sort of our stamp that we're stamping out everywhere in the data center. And so we still have this unit that we can think about homogeneously. We can do the same sort of monitoring on all of these. We know that code that's deployed to one of these units can be deployed to another one of these units.
Thanks. Maria is giving me the wrap it up symbol. And so I have so is there anything that the audience would like to ask or get off there to no? Oh, good.
C++. So are we going to write C++ code that runs on heterogeneous hardware pretty soon?
We were talking about that for quite some time. Yes.
It's something that's going to evolve, and Tom made a good point that I'm going to reuse, which is that we're talking about performance portability or productivity, all these different metrics, all these P's that people like to talk about. One of the things that I think that we'll see as a result of modern C++ is if we get greater productivity, you will be able to move between platforms more rapidly. And that doesn't mean that you'll write the same code and run it everywhere and it'll perform great. But if you can modernize your code with a specific vision for high performance in a parallel environment, then you can specialize as necessary and potentially go after novel technology. And there's enough of an abstraction layer there that your pain as long as you've thought about the design, thought about concurrency all the way through, and data locality, that your pain will be modest but finite. Whereas today, I think, if you go to the bottom and start with your C89 or your Fortran, or you're just terribly written C++, you're going to have pain in every single vector you go in. So we need to sort of kick it out of the bad local minima and go look for the and what we'll find, I think, is the global optimal solutions for modern hardware will be closer together than a lot of these sort of bad local minima are today.
I'll try to make a summary point that I think the whole panel will agree to. I think there's two things you want to do if you're writing your own code. And so you're not doing AI necessarily, so you're using a framework and a neural net. But if you're writing your own code, you want to focus on data locality and compute intensity. If you do those two things and you can get that to happen, you can take advantage of FPGAs. You can take advantage of a multi-core CPU, because anymore, right, the latest CPU had 24 cores? 28 cores. So, if you had data locality and compute intensity, you can take full advantage of that. You can take full advantage of a PCI-connected FPGA, a PCI-connected GPU, a PCI-connected almost anything else. I mean, at a high level, your heterogeneous architecture is a multi-core CPU with a PCI connected to something. So if you've architected with data locality and compute intensity, you're going to be pretty well good to go. And C++, as it evolves, and I think most of the community, vendor community, are pushing in a direction, I think you get to success. And the challenge, of course, is a lot of the code we have to start with does not exhibit data locality or compute intensity. But I think that's the target to focus on, and we can all kind of rally around.
So I think that's a really good point. And I wanted to switch over onto the hardware side of that, which is that what I'm hearing, I think, is a lot of maybe a bit of hesitation or fear around these new heterogeneous architectures and things like asking questions like whether going to AI is the right solution for your applications. And I think the thing is, a lot of these devices are being made and sort of marketed for these type of applications, but fundamentally they are compute devices with some amount of computational capability, some amount of memory bandwidth. And so the same way that you can tune your applications for data locality and these sort of things, I think you should look at the hardware as essentially these things that have different ratios of I/O capability, compute capability, and sort of just to point that out, I mean, the neural networks have really gained a lot of steam from using GPUs, but I mean, remember, GPUs at one point were graphics processing units. That's what they were designed for, but fundamentally they could do, essentially, still are, but you can do very fine-grained parallel processing on them. Fundamentally that's what they're doing, and they were able to take advantage of that. And so in the same way, the neural net stuff coming out, a lot of it is fundamentally just doing linear algebra, maybe with high memory bandwidth, maybe at narrow precision, but that's something to keep in mind. Take a look at what fundamentally these devices are doing and see if you can cater your traditional applications into those.
That's interesting. Excellent. Thanks. All right. Are there other? I think we are. Oh, of course.
We built some heterogeneous stuff, and we for different markets, for different reasons. One of the reasons that Intel builds graphics in client parts is because it was and it's not super awesome Hollywood movie graphics, but it's really cost-effective, low-power graphics. That was a response to a clear market need to do something. What do you want? Like, the answer may be no, you're not going to get it. But if you could glue stuff together, what would you glue together? If you build a heterogeneous chip, would you have it be a multi-chip package with a CPU, an FPGA, a GPU, and a DSP on it, and an integrated NIC, and 16 stacks high and cost $35 million? Or what is it that you'd want? I mean, I'm curious, because I talk to people, and some people are like, yeah, I really want a tightly integrated FPGA, and other people are like, no, 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 I want to have the PCI attached thing for all these other reasons. I guess, you know, you all have to have, like, you know, Christmas lists of what hardware you dream of people making that you're not getting. What is it? Is there something you think that, you know, somebody should make, but what is wrong with these vendors? Why don't they just make that? I don't know. What's your Christmas list for hardware? Which so a high performance interconnect between your heterogeneous cards.
I wanted tremendous amounts of processing, tremendous amounts of storage, very close to the processor. How about
Storage close, so tightly, so NVDIMMs.
yes,
More than that.
NVDIMMs, but NVDIMMs in reasonable size and a good connection to. So I want and a relatively seamless network stack. So basically, processing, storage, and a way to refresh it in a short, low latency point of time.
And for networking, you mean TCP/IP or SPI, or you don't care?
What I'd like is TCP/IP because we have some MPI applications, but it's really like
No, that's totally legit. I'm a big part of the MPI community, but I also recognize MPI shortcomings. So if you say it's TCP/IP, we make NICs for both.
Okay. Oh, does he? Oh, Nico says. Nico first. He has a great T-shirt. Oh. Oh. Okay, yeah. Okay, great. I'm full. Nico.
Sorry about that.
Right. So I wanted to second this a bit that in view of systems, what I would really like to have is in view of systems where I don't know which technology my software colleagues will be best able to exploit. This will change. Something which is disaggregated and can be composed by and combined with a fast fabric would be very nice. If the uptick because of that fabric is not so high that it sort of voids any advantage I get from that. No? So, I mean, in cost, obviously. But that would be really very useful if we could combine it. And as things evolve, people learn to use things. I can add GPU power, FPGA power, and or memory. You know, this would be really very helpful. Yeah.
So tightly integrated and disaggregated.
Well, tightly integrated, yes. I mean, okay. I mean, I understand that this requires that the workload is not too latency sensitive. There's a price to be paid if you want to fabric interconnect it, for example, NVMe or fabric. But that I think this can be arranged for many of our workloads. They can be made throughput oriented.
So bandwidth is much more important than length.
Bandwidth is key, yes, and that's why I'm not really convinced about TCP/IP. I mean, I think that TCP/IP is horrible for high bandwidth applications. But I pass it.
So looking at how we are struggling with some of the with using the hardware that exists, at least the Intel variants with huge vector units, I have a retrograde thought that would it be easier, or can't we get something that doesn't have this waste for us in the huge vector units that does only the regular XMM maybe at most, but it has memory which is very close to the compute unit itself, and does it practically whatever we had 20 years ago, but on a much smaller scale, and just on chip.
Before he answers, I want to go back to Nico's point. So you said you want lots of bandwidth, but don't care about latency. And you want something that works like it did 20 years ago. And one of the challenges that the vendor community has when we look at the HPC community, and actually Dave Turek from IBM had a great chart on this, which they charted out all the algorithms that are used in HPC and put them in a cube. And it's pretty funny, the cube had a little dot for LinPack. And then it had, you know, something like HPCG, and it was really big and filled up part of the cube. And then it had another algorithm, and it filled up another part of the cube. And pretty soon you see almost all the cube is filled up with all these different requirements. And the challenge is that the HPC community needs just about everything. We need high bandwidth and low latency, and it needs to be tightly coupled and disaggregated so that we can do just about almost anything. And not being tongue-in-cheek, it's a challenge because the real algorithms look that way. And it's not that anybody's being trite, because a different, you know, if I was in a different audience with a different set of problems, they would need very low latency, and the bandwidth. Everybody needs high bandwidth, but it's just it's a challenge in the vendor community that we have. And I go back to your comment, which, and I've used this analogy before. Look at where the commercial community is going, and line up behind it. You know, you think of a bicycle race. The bicycle racer is Google. Get behind them, and if your algorithm can look like that, if it, you know, then you're in pretty good shape, right? And if it doesn't look like that, I want to scratch your head and go, how can I change it so it looks like that? And I think you're absolutely right. You know, there's nothing in AI it's just sparse linear algebra, for God's sake. And so it's not like it's anything magic. So if your problem can look like sparse linear algebra, a lot of compute intensity, you're going to be in good shape. Right? You know, and I think what your requirement there for, you know, those sorts of things, if we can look at that in the context of what is the broader commercial market want, I think we can get something put together that'll work really well.
So I've multiple anecdotes about vectorization. So one time when I was a customer, I was asked by IBM actually to talk about, well, like, what's the optimal SIMD length, and we basically I did this with Livermore, and we basically said, okay, vector unit of 1 is universally applicable. 2 is pretty good because you get complex numbers. 4, not really that useful, but if it's for free and you get more efficiency, you know, 8. And then infinity. And infinity was just a proxy for GEM, for matrix multiplication. So 1,000, you know. I could use a SIMD unit if I could do 1,000 FMAs at one time. I could use that for all my matrix tensor stuff. But so the good news I can tell you is it's not as wasted as you think. If you look at something like Skylake Xeon Scalable and ABX 512, if you don't use ABX, so if you use ABX 512, it runs at the power limit, and the frequency responds. If you're running on all the cores with full vectorization, you're really getting warm, and that thing has to downclock a little bit. If you run a bunch of scalar SSE2, that thing says, hey, I'm not using anywhere near all the transistors. I have power to burn. Let's crank this puppy up. And so if you look at, and it's interesting from a performance analysis perspective, the HPC people and all their peak numbers are going to get totally screwed up by this. But, you know, I've run code where it turns out ABX2 code is the fastest. And that's because the trade-off of going twice as wide a vector versus the frequency I give up because of the power cap, it turns out that the Pareto optimal point is at ABX2 vector code. And so this is something that has come up a lot in the, you know, in the hardcore HPC world. We're talking about dark silicon, and that's really what heterogeneity is about at some level, is we can put more transistors on a die, and together, the vendor community can put tons of transistors on a node, maybe more than you can power. And at that point, specialization becomes a great thing because it means you can get better efficiency, but then when you don't use it, you know, and I think one of the things that people should think about is whether or not your heterogeneity has the right TCO trade-offs. You know, FPGAs are lower power, in power efficiency can be really, really good. So you can deploy an FPGA at a lower power envelope than maybe another accelerator. On the other hand, last time I checked, the retail prices on FPGAs are not low. But so thinking about, turns out AVX512 is almost free acceleration, because if you don't use it, you're not burning the juice versus something that's a separate thing. But anyway, so it'd be great if we could have
So can I make an operational comment here? The grid's not as homogeneous as you think. You land at my site and you're running on 4 generations of Intel and 2 generations of AMD. You could be running on an 8-core machine, a 12-core machine, a 24-core machine, a 32-core machine, a 40-core machine, a 64-core machine. We already have a fairly, okay, it's all Intel, or it's all x86-64. But those systems are very different. And I remember an instance where, anybody know what VOM's proxy is? Yeah. So VOM's proxy broke because they converted it to Java. It ran on our machines that had 64 cores and 128 gig of RAM. Java, when it starts up, says, I'm going to steal 50% of the system memory. So 50% of my system memory is 64 gigs of RAM. You're only allowed to have 8 or 12 or 16. You're getting killed. So suddenly everybody was trying to check the proxy or net the proxy, and their jobs failed because they're not allowed to run on those systems, because Java's trying to consume half the memory in the system. Right? So we already run in a quasi-homogeneous environment because none of the machines that you land on are the same. This is not, so again, speaking from at least the UK standpoint, these are not HPC facilities. Right? You don't buy one set of CPUs and across the whole thing. You're landing on 6 procurements every year. And those CPUs are different, those systems are different. Some of them have 7200 RPM disks, some of them have 5400 RPM, some of them have SSDs, some of them have 2 gigs per core, some of them have 4 gigs per core, some of them are hyper-threaded, some of them are not hyper-threaded, some of them have extensions that you want to use, some of them don't. So making these low-level performance metrics is an interesting standpoint when you land on a site that you don't control all the components.
I just want to know if you've ever looked at the x86 instruction set and you're like, why don't they just get rid of all the crap? That's why. You don't get rid of anything because it would break his life. And that's bad. Anyways.
I believe that Gordon had an informal event scheduled later, and I think that we are a few minutes from standing between people and beer, which is never a safe place to be. So I would suggest that we thank the speaker, the panelists. Thank you all.